Hey, Mr. Schwarberg here. We are going to go ahead and look at some rate graphs. We're going to interpret them in context and answer some questions about some graphs. Okay, so let's go ahead and get to it. First of all, what are rate graphs? Well, graphs of rates are common in calculus. Now, while the horizontal axes in such graphs may stand for many things, it's often time. So generally down here, you're going to see this axis always represent time in rate graphs. Okay, and they're called rate graphs because the vertical axis will often be some type of rate. Okay. And in rate graphs, a point on the graph represents a value at the indicated rate at a certain time. So something per something, right? A slope, which is a derivative, represents the rate of change at that indicated rate. So a certain amount of rate per whatever the x-axis is, right? Or per rate, and then at the end we'll also have to include the x-axis. Okay, and the signed area between the graph and the horizontal axis represents the definite integral, which is also known as the accumulated area or accumulated value. Okay, and in this context, the integral is thought as the accumulator. So we'll look at some of these examples and we'll analyze, okay, what does a point mean on a rate graph? What does a slope mean? And what is the signed area? Okay, so here is the first example. And it says the graph at the right models the rate of rainfall in inches per hour. Okay, so that's important, in inches per hour from midnight until 6 a.m. Midnight until 6 a.m. So what that information is telling us on our x-axis is that here at time 0, this is midnight, 12 a.m. all the way to 6 a.m., which will be 6. Okay, and our rate is rainfall in inches per hour. So 15 says, write a complete sentence to explain what point A on the graph represents. Include the numbers and units in your answer in this example and then in some future examples. So here's point A. Okay, so I want to represent, what does that mean? Well, it means, okay, and notice that that's at t equals 3. So at 3 a.m., it is raining at a rate of, what is that value? 1 inch per hour. 1 inch per hour. Okay. 16. What is the slope of the graph between points A and B? So here we can go ahead and look at A and B and notice that slope, it's a horizontal line, so our slope is 0. Now 17 says write a complete sentence explaining the meaning. So what does that mean? Well, it just means from 3 a.m. to 4 a.m., right? The rate of rainfall did not change, or that it was constant. Okay, so I can say from 3 a.m. to 4 a.m. There is no change in rainfall. All right. Okay, question number 18. It says, what is the slope of the graphs between B and C? So here is B, here is C, and we can calculate slope, right? That's rise over run. So I go down 1, 2, 3, 4, 5 units. Okay, so down 5 units, and then I run over 1. Now, be careful. Although I'm going down 5 units, how much did I actually go down in terms of the context of the problem? Well, I mean, up here, this is 1 inch, right? Each unit is 0.2 of an inch. So really, our slope is -1 over 1. So our slope is -1. Okay? Now we want to go ahead and write a sentence explaining the meaning of our answer. So, okay, well, we can say from 4 a.m. to 5 a.m. the rate of rainfall decreases at a rate of 1 inch per hour. Per hour. Excuse that phone call. This is, sorry, 1 inch per hour per hour. Now, why is it 1 inch per hour per hour? Well, again, the inches per hour, that's your delta Y, right? That's the units placed here, right? This is inches per hour, right? That's our rate. That's what an individual point represents. And then per hour is our delta x. So you'll see it written like this. You may also see this written as a rate of 1 inch per hour squared. You'll see that. Or you could go ahead and again, if we go back to our notes up here, right? Here, so 1 inch per hour per hour. You might also see it written that way as well. Okay. Next, find the integral of r of t from 3 to 5 dt. So what they want here is they want the integral. And remember, integral is the area underneath the curve. So my bounds are 3 and 5. And so it happens to be just that red signed area here. Okay, and if we want this, right, all we have to do is go ahead and calculate this. So we'll just go ahead and calculate these using just our general shape formulas, right, or area formulas. So length times height, okay, so of that rectangle. So I have 1 inch times 1 hour, okay, plus, and over here again the height is 1 inch per hour, and then divided by or times our unit here, which is also 1, and I want a half of that because that's a triangle. So this gives me 1 plus a half is 1.5. Okay, so there is your area. All right, write a complete sentence to explain the meaning of our answer to example 20. So what does that mean? And I want you to first just consider from 3 a.m. to 4 a.m. Okay, in this area, right, the rate of rainfall is 1 inch per hour, and one hour has passed. So how much rain has accumulated? Well, if the rate is 1 inch per hour and 1 hour has passed, that's 1 inch, right? So that just represents the amount of rainfall. Okay, so we're going to go ahead and say this. We're going to say from 3 a.m. to 5 a.m. there was a total of 1.5 inches of rainfall. And that's why the integral in these rate problems is called the accumulator. We just analyzed how much rain had accumulated, right? And that was 1 inch. Okay, number 2 or 22. Approximate the value of the integral from 0 to 6 r of t dt using geometrical regions and show computations. So what we're going to have to do here, from 3 to 5 was no problem, right? Because those are solid geometric shapes. What we have here for from 0 to 3, though, is we have a curve, okay? So we're going to have to approximate. Now, one method to do this is I can just go ahead and connect a straight line here. It's kind of straight. Okay, and I can approximate this. Now, this is not going to be, again, exact, right? Because notice and I'll put this in green. Notice I'm, well, put it in gray. I'm leaving this out. Notice I'm leaving out this little area, and I'm leaving out this little area, but I'm also catching some of this area here, right? I'm accounting for this, so it's not actually there. So we're going to be close. It's approximate, right? But with that straight line, I can go ahead and I can compute the area, right? So from 0 to 3, okay, that's 3, and then the height of this shape is again 1 inch. So 3 times 1 times 1/2, okay, plus, so this is from 0 to 3. I also have the integral from 3 to 5 of r of t dt, and we said that that value was 1.5, right? So 1/2 of 3 is 1.5, so this is 1.5 plus 1.5, which is 3. Okay, so there's our signed area. And then again, write a complete sentence explaining this meaning. Well, this just means that from midnight to 6 a.m. Oh, I'll come back to this. From midnight to 6 a.m., there was a total rainfall of 3 inches. So notice I just said midnight to 6 a.m. Our integral in 22 didn't account till 6. It went from 3 to 5. So let me just adjust this bound. And you're like, Schwarberg, that's not what you calculated earlier. I know that. I agree. But let's go ahead and look at 5 a.m. to 6 a.m. Notice that my line here is right here. Well, it's black on black. You can't see that. It's from here to here. So how much rainfall occurred from 5 to 6 a.m.? None, right? So I can add a big fat 0, and it doesn't really affect our answer. So 3 inches. All right, that is rate graphs. Remember, we went ahead and looked at a graph such as this, right? This represents a rate, right? Usually a value over a time, right? Okay, inches per hour, and then we also have another x-axis, which is also hours. So this represents a rate. Okay, now if we take a derivative, what we're doing is we're analyzing the slope, right? So that's the derivative of the rate. And then if we take an integral, again, that's the area underneath the curve. Okay, all right, I'll catch you next time. Thanks for watching. Peace.